This video is about domain and range and finding those from either a graph or from an equation. Just as a refresher, a domain is the set of all possible x values that a function can take on. The range is the y values that a function can take on. Our book tends to focus more on interval notation when denoting domain and range, so we're going to work on that now. When we're reading a graph, we read the domain from left to right, in other words, on the x-axis. And when we look at the range, we're going to look from the bottom to the top on the y-axis. We're going to denote the domain as a capital D, and we'll denote the range as a capital R. So let's look at this first example. We want to find the domain of this function. In other words, what x values can this take on? When we look at the graph, we notice one, it has arrows at the end, which means it's going to continue probably in the same fashion. But when we look at the x-axis, every time on an x-axis, we're going to have a y value associated with that. We don't have any gaps or holes. So in this case, it's minus infinity to infinity for our domain. For our range, though, we notice that the smallest y value that we seem to be getting here is -3, and that we really max out here at +3. We don't appear to be getting any bigger. So we're going to use brackets because we're going to include our endpoints, and our range for this function is going to be from -3 to 3. And of course, we're assuming that this is just repeating in its same fashion. Let's look at our next example. This one also has arrows on the end. So it might appear that this is stopping here at -3 on the x-axis when we're looking at the x-axis. But in truth, if I was here at 3, I would just be very, it's going to keep going. It's just going to take a long time to get over to the -3, and same for the other one. So here, our domain is also -infinity to infinity. And our range would be the y values that the function would take on. And since it goes up forever and down forever, our range in this case is also -infinity to infinity. Now moving on to this next one, we notice that at the end point, we have a solid dot here. That means that's going to end. So when we're looking at our x-axis, as we follow along on the x-axis, the first time we even have an x value is at -4. So our domain is going to be from -4, and then based on the arrow, to infinity. Our range, on the other hand, if we're following our y-axis up, we don't have any function values until we get to y is 0. So we'll have from 0, and it keeps growing, so 0 to infinity. Pause your video and see if you can find the domain and the range for the remainder of these functions. Let's take a quick look at these. When we looked at this first one, we should notice that these arrows on the ends are going to the left forever. So we're going to have an x value all the way back to -infinity, but we're going to stop when we get to the 4, and we're going to include the 4 because it's a solid dot. We also may notice that because these arrows are going down slightly and up slightly, our range is going to be -infinity to infinity. On the next example, you kind of had to notice that there was an asymptote here. And so in this particular case, our domain skips over that number 2 because on the x-axis, we have function values, but not right there at -2. And then after -2, we have function values again. And similarly for our range, we're going to skip over 0 because that is also as an asymptote. And we're going to skip over that, and then it will continue on again. The last example here was just a line, and its domain and range were both -infinity to infinity. I have just a few more examples here. For this first one, g of x, notice that we have these solid dots at the ends. When we're looking at our x-axis, we notice that on our x-axis, we don't have any function values until -2, and we're going to stop having things at 4. So we're going to have function values all along here, but once we get to 4, we're going to stop. Our range, on the other hand, when we're looking at the y-axis, the first time we have anything is when y is -1, and we're going to stop when we get to up here, which is 3. On this last one, you should notice that this is a solid dot, but this one over here is an open dot, meaning we're not going to include it. So our domain on this one, we're not going to have anything on for x's until we get to -3 inclusive, and we're going to stop when we get to 4, but we're not going to include that because it's an open circle. That means we're going to get as close as we can to 4 from the left, but we're never actually going to reach 4. And for our range, we notice that we have our lowest value here is at -3, and it's inclusive. And we can have function values all the way up. Our maximum here, it looks to be 2, also inclusive. So we want to be able to find a domain and range looking at a graph, but more often than not, we're going to be looking at an equation. And in general, the domain of a function is all real numbers unless there is something that creates a situation where your function is not defined. And there's only 3 things that can happen that might cause something to be undefined. And those 3 things are division by 0, the square root of a negative, and the logarithm of a negative number, or 0. Those are all bad. Now, we're going to primarily be working with number 1 and number 2 because we haven't learned yet what a logarithm is. But I want to add it to the list because I don't want us to forget that when we get to logarithms that we are going to have to pay attention to that. So, let's take a look at some examples. The first example I'd like to show you is something where we have an x in the denominator. So, if we have this function f of x equals x plus 3 divided by 8 minus 4x, we might think that the domain was all real numbers except things that are going to make that denominator 0. So if we set that denominator equal to 0 and say it cannot be 0, we're going to get 8 is equal to 4x, or x is equal to 2. So what we're going to say is x cannot be 2, and our interval notation would be from -infinity up to 2. We'll skip over that 2, so we'll say union, and then 2 to infinity. Because that is the one number that would make it 0, so that is the one number that we have to skip over. Let's take a look at one that has a square root. So in this one, we know that we cannot take the square root of a negative. So we need to look at this, f of x equals the square root of x minus 6, and ask ourselves, what's going to make that negative? Well, in this case, it's a little bit easier for us to say we want the x minus 6 to be greater than or equal to 0. So x has to be greater than or equal to 6. That's what anything that's bigger than 6 is going to be okay. So we're going to say from 6 to infinity is our domain. So I'll write domain up here. We can say that this is the domain down here. All right, let's take a look at a few others. Finding the range of something is a little more difficult, but we could visualize the graph to help us understand what the range is. Let's take a look at these 4 examples and decide what the domain and what the range are. To do that, we're going to mentally go through our list of things that cause problems. So for part A, we're going to ask ourselves, do we have any division in this function? And the answer is no, so there's no division by 0. And then the second question is, do we have any square roots? No. And if we don't have any problems, then the domain is going to be all real numbers, minus infinity to infinity. This graph, if we use our graphing calculator, is going to look something like the following. And we'll notice we have arrows on either end. So in this particular case, our range is also minus infinity to infinity. Looking at part B, we have an absolute value of x plus 3. We have no division and we have no square roots, so our domain is minus infinity to infinity. This graph happens to look like a V shape shifted up 3. And again, we notice that the arrows are going up forever. The smallest y value is going to be -3. And then it's going to go on forever, so that will be infinity. On our next example, we're not going to worry so much what the graph looks like. Let's just find the domain. And this is a little different. We notice that yes, we have division, and we know that the square root of 3 minus x cannot be 0. And we have a square root, so we know that 3 minus x, what's underneath the square root, or the radicand, has to be greater than or equal to 0. Only in this particular case, we know it can't be equal to 0, so we're just going to take 3 minus x greater than 0. If we solve this, we get 3 is greater than x, or flipping it around, x is greater than 3. And in interval notation, that would be from 3 to infinity. Notice we're not including the 3 because the 3 is what makes the denominator 0. For our last example, we do have division, and we know our denominator cannot be 0, so we're going to set it equal, or actually not equal to 0. And in this case, we'll factor it, and we should get x minus 5 and x minus 1. And if we solve that, setting each one equal to 0, or in this case, not equal to 0, we know that x cannot be 5 and x cannot be 1. So our interval notation for our domain is going to be negative infinity up to 1, union 1 up to 5, skipping over 5, union, erase that comma, union 5 to infinity. Let's take a quick look at an application problem and see if we can use function notation and think about the domain and the range of this function. In 2014, a widget from Acme Widget Makers had a cost of $23.63. In 2000, a widget from Acme Widget Makers had a cost of $17.39. The cost of a widget from Acme Widget Makers can be estimated by the linear function c given here. C of x equals 0.4306x plus 11.0043, where x is the number of years since 1985. That means that c of 10 gives us the cost of a widget in 1995. We want to use the function to predict the cost of a widget in 2018 and 2025. So for starters, how far away from 1985 are 2018 and 2025? So we're going to do 2018 minus 1985, which is 33, and 2025 minus 1985 is 40. So C of 33 would tell us the cost 33 years from 1985, and using our function notation, we would plug that 33 in, and we would get a final answer of 12.46398. So the cost in 2018 is $12.46. We can also find the cost in 2025 by plugging in our 40 and getting 12.765. So the cost in 2025 is $12 and we'll round 77 cents. We can use this function also to find when the cost will be approximately $32. So we'll take our function c of x here and we'll plug the 32 in for the cost. So we have 32 is 0.4306x plus 11.0043 and solve for x. Solving this is going to give me 48.759. This is the number of years since 1985. We will round this to 49 years, and we will add 1985 plus 49 and have in the year 2034 the cost will be $32. We can find some of these values on our calculator. If we want to find these on our calculator, we can solve the equation for y, or alternately our function value, in this case c of x, and input the equation into y1. So you do that by going to y equals and then typing your equation, and then using the second function, which is the blue key, and clicking on trace, and you'll notice above trace it says calculate. You can choose number 1, which is a value. It will graph your function. In this case, this is a linear function. and it will pop up at the bottom with x equals, and it will ask you for an x value here. So if you were to plug in 33, it would give you y equals 12.46398. Okay. Then if you want to find x is 40, you simply have to type 40. It will overwrite the 33 and give you the next value. Let's talk about the domain and the range of this cost function. In this particular case, because it is an application problem, the domain are values that make sense. Because we are told that the x values represent number of years since 1985, we're assuming that's from 1985 on, not years prior to 1985. So our domain, x, would be 0, and assuming that the world continues to be, domain would be 0 to infinity. The range, on the other hand, if we were to plug 0 in to our cost function, our smallest range value would be 11.0043. And again, assuming the cost could increase without bound, that would be infinity. That concludes this video on domain and range. Thank you.